Well, thank you very much for this introduction. It's a great pleasure to be here. Good afternoon to all of you. I'm particularly pleased to see so many young faces in the audience, which is not usually the case in distinguished lectures where one talks to the converted and to the faculty. But I welcome this opportunity to also reach out to the younger colleagues to hopefully interest them in an extremely fascinating and important topic, namely to understand urban from a systems perspective. I have been much impressed by a lot of the work going on here in Imperial College. I have also benefited enormously in learning from the research being done here, and I've benefited from the good humor and the untiring work ethic of some of my colleagues. I have here three distinguished contributing authors of the urbanization chapter of the Global Energy Assessment here sitting in the first row. So thank you very much. This is all, as Professor Pachauri, the head of the IPCC, always calls it, this is a labor of love, these international assessments. You don't get anything paid, but we hopefully were able to produce some new insights. These insights I'd like to phrase today as a quick kind of précis or summary overview of the urbanization chapter. I'll also flag some of the publications where you can find more material, and I try to stay within 40 minutes as indicated, so we have some time for discussion. I particularly also encourage the younger colleagues to join me with any questions on any topic you would like to discuss afterwards at the cocktail reception. I'll speak with the senior guys afterwards at dinner, so the cocktail is your time slot, so come and speak to me, please. So, I would like to introduce first this global energy assessment. This is a multi-stakeholder kind of international science assessment with a focus on energy, so a little bit different from IPCC, which has its focus on climate change. This assessment had a decided energy focus, but it was structured very similar in terms of organization, a kind of peer review process and recruitment of authors like the IPCC. It ran for almost 4 years, involved hundreds and hundreds of scientists as lead and contributing authors, and obviously also as reviewers. Like in all of these assessments, you take first stock, and so also the global energy assessment is not different. You first review what is known out there in terms of the energy challenges, what are the major challenges facing global energy systems, what options do we have available to respond to these challenges, and how do we can combine through policy frameworks these options in managing transitions to new states of the energy system. A specific feature, and this is a little bit unlike to the IPCC, where the work is, as was mentioned earlier, organized in different very distinct working groups with where interaction and analysis of interlinkages is always a challenge. Right from the onset in the global energy assessment, we had the objective to look at linkages. The linkages provided between different kinds of energy objectives, the energy options and the transition strategies which are needed to make use of these options. And some of these linkages focus around the issue of energy access and poverty, energy development, energy security, health, and climate change. Last but certainly not least, and this is again a little bit different from the IPCC, is we were not under governmental control, so we actually could venture into policy guidance. So we also did normative scenarios, normative in the sense that they describe desirable outcomes of global energy systems, and then do a back kind of reverse calculation in analyzing what does it take to achieve this desirable outcome. So this is a very normative scenario exercise, and I think it was very interesting to try to do this. So not the usual thing that you do first descriptive scenarios, and then you ran out of time, and you cannot run any policy scenarios anymore. And the reason why I mentioned this assessment today is that it is the first international scientific assessment in which urbanization was devoted a separate chapter. Quite surprisingly, we had Millennium Ecosystem assessments, we had various rounds of IPCC assessments, and urban actually never took center stage. So this is the first assessment where urban took center stage, and We have a lot of publications coming out of it. I circulate some of the documents. So this is this summary for policymakers and technical summary. So I'll please distribute it amongst it. The full report is also available. You can grab it in David's office. It has 6 kilograms, so you don't want to let it drop on your feet. But the good news, of course, is you don't need to tackle 6 kilograms. All of the report is available on the internet, www.globalenergyassessment.org. All of the chapters, all of the supporting material, all of the data sets are all posted there. So a great resource, especially for younger colleagues, to catch up and read different type of topics. In the urbanization chapter, we were not satisfied with the page limit imposed on us by the GEA authorities, so we produced a more extended version of the chapter as a book published by EarthScan, edited by David and myself, and also circulate this book amongst yourselves so that you can have a first look at it if this, whether you want to use it in your classes or coursework or as browsing, because it contains more material than was possible to produce in a more condensed volume of the global energy assessment. So in today's talk, I'm going to try to run you through the main conclusions of this assessment, again highlighting some issues but in a very selective way, because there is enough material out there for you to dig deeper into it. And if you have more specific questions, I welcome these specific questions later on in the discussion session. I think the first major conclusion is not a new topic, but it perhaps explains why we take an interest in urban issues from a systemic perspective. We take an interest in urban issues because the world is already dominantly urban. We all know the UN statistics that more than half of the world population lives in urban areas. That's a very significant statistic because has never happened in the history of humankind that we have such a large concentration of the human population in urban environments. But this is only one perspective. It's a demographic perspective. And as I will show you in a second, when we look at other indicators, when we look at energy use, we look at GDP, when we look at communication and infrastructures, actually the world is already much more urban than the population numbers seem to suggest. According to our assessment, the world, energy-wise, is already 3/4 urban. 3/4 of global final energy use are actually happening in urban environments. And so therefore, we need to understand urban, we need to understand urbanization, and we need to bring systems perspectives into the analysis of urban systems, because urban systems are messy, are complex, and cannot be reduced to simplistic notions as single-purpose energy systems, because energy is used for a particular purpose. Energy is not an end by itself. Energy is here to provide services for economic activities and the population, and we need to understand these interrelationships. So from this perspective, urban is the dominant form of spatial organization of our societies. And if we talk about any of the major challenges in the next sustainability transition, whether we talk about poverty, whether we talk about economic development, whether we talk about empowering people, whether we talk about respecting planetary boundaries, whether we talk about climate change mitigation, all of these challenges need to be answered in an urban setting. It is relatively easy to conceive sustainable systems in a low-density rural setting. It is very challenging to consider these systems in an urban setting. It is challenging, but at the same time also extremely interesting. The downside, or the reverse, it is related to rural areas. If the world is already dominantly urban, then of course we need to also think about what happens to rural areas. And as we will see in a second, actually rural populations are going to peak within the next decade and are then declining. So all of the future momentum will be in urban areas, which adds emphasis to the need to understand these systems a little bit in more detail. I have assembled you here some of the indicators which we have developed in our chapter to describe urban systems. Obviously, you need multiple indicators, and I show you here a few. One is land use, one is demographics, population, one is GDP, one is final energy use, one is light luminosity, as measured through satellite data, and one is on the internet infrastructure in terms of internet router density. Now, as it turns out, in the assessment, or many of you will be very familiar with this kind of problematic, is that we do not have data on urban systems. All of our statistical reporting is unduly influenced by the national nation state and the national system of accounts as codified by the United Nations ever since the 1920s, or the then former UN League of Nations. We hardly have equivalent statistical reporting system in an urban context, which makes the analysis of urban systems quite apart from all of the intricacies of where you actually draw a system boundary around an urban system, which is a challenge by itself, very, very difficult. Now, of course, sometimes we have measured data, like remote sensing data, but as this table actually shows you, when you look at the uncertainty range of the estimation of urban land coverage, the literature actually gives you value between 0.2 to 2.7% of the global land surface as being classified as urban land uses. So that means whatever we can measure is actually affected by the largest uncertainty range. This is an uncertainty range of a factor of 10, which shows that there is no easy remote sensing shortcut to trying to understand urban systems, which means we need to question ourselves in terms of where do we collect the data, how do we collect the data, and how can we bring, for instance, already existing data sets, very often in the private sector, geomarketing being one of the many, many useful sources to bear for scientific analysis and modeling studies. So this is a much longer discourse, of course, which we need to address over the next couple of years, but it is a very important one. Because right now, we basically navigate very, very often in the dark. According to our assessment, we have very detailed data on less than 24 of cities worldwide, and these are all mega cities, cities like London, cities like Tokyo, which has fantastic data sets, but even cities in China, like Beijing or Shanghai. For these very large mega cities, we do have data, but for everything else, we do not have very, very much data. And this is a very serious problem for our analysis. Now, when we look at population, I have mentioned a number already. So these are data benchmarked to a common base year, which is the year 2000. In the year 2000, 47% of the world population used to be urban. Right now, this ratio is close to 51%. So we have crossed the 50% threshold already. And you see also how this kind of assessment or statement is affected by different system boundaries, which you can adopt, whether you take an administrative region or whether you take a more functional definition of an urban system boundary. And so therefore, there is some uncertainty range, but actually this uncertainty range from a demographic perspective is not too large. According to our assessment, it's approximately between 44 to 52% in terms of urban population. Let's move to energy. According to our assessment, 3/4 of final energy use. So this is final energy use, not primary energy. Some people, like the International Energy Agency, have also produced estimates for primary energy. But according to our assessment, these estimates are affected by much larger uncertainty and error margins. And so therefore, we decided to focus on final energy, which we believe is a much more useful measure, also because it is much closer to the ultimate purpose of the energy system, namely understanding energy services, which is not necessarily the case always when you look at primary energy. So the uncertainty range here is a little bit larger, 56 to 78%, underpins this estimate, this central estimate of 76%. But you see how important urban systems are in terms of energy use. And the reason for that is this high energy use fraction is explained by the economic powerhouse which cities are. Basically, 81%, according to this estimation, of the global GDP is actually generated and consumed in an urban system context. So cities are dominant in terms of economy and in terms of energy use. And as the last number shows here, when you look here, 96% of all internet routers are also located in urban centers. So it means even the internet, which we think normally of not being a very, very place-specific kind of infrastructure because it's virtual, server farms can be everywhere. Actually, when it turns out, when you actually look at the actual location of server farms, this is a limited data sample of only 600,000 internet routers. They are predominantly in urban areas, according to our estimation, 96%. So that means that also our communication infrastructure is first of all determined in an urban context, and also its vulnerability is defined through an urban context. If cities are vulnerable, then also our communication and other technical infrastructures become vulnerable. Yet another reason to look at urban systems. So this is the projections which we have done. We have developed different kind of scenarios, and these scenarios are contrasted with this single projection of the United Nations. This just gives the global aggregate numbers in terms of urban versus rural population. Now, obviously, we have uncertainty. We have here different scenarios of urban population, and we also have scenarios of rural population. But the important conclusion is that invariably in all scenarios, the rural population peaks before around 2020, 2025, and then declines thereafter. So we are really at yet another watershed historical transition point in human history. Not only we have more than half of the world population in cities and growing even further, people leave the countryside. And this is, of course, the combined effect of demographic reproduction plus migration, but this is a very robust finding across all the GEA scenarios, and it is also reflected in the UN population division projections. So a very important guidepost for the next 20 to 30 years, because this decline of the rural population adds further pressure, migration pressure, to the growth of the urban centers, particularly in the developing countries and particularly in Asia. So we will see from a historical perspective unprecedented growth in absolute numbers of urban populations. How to deal with this unprecedented growth in terms of infrastructure requirements, in terms of housing, in terms of energy, in terms of water, in terms of preservation of habitability, of local environments, air quality, for instance, is one of the greatest challenges of sustainability. It is not the long-term target. The biggest challenge of sustainability will what to do with 3 or 4 billion additional people in urban areas over the next decades to come. This will be one of the greatest challenges, in my viewpoint, especially for systems engineers, if we want to house these people in an appropriate and equitable manner. A second important development, which we need to also reflect in our analysis and also in our methods, is that the urban phenomenon is pervasive, and it is fractal. It affects urban centers at different size categories. In our traditional discourse, we have focused a lot on the growth of megacities. These are very symbolic, they're very visible, they're huge, they're frightening in terms of their complexity and sheer size, so everybody looks at these megacities. But as it actually turns out, megacities are only a small sliver in the total urbanization phenomenon. You see here, this red bar here, these are the megacities defined as being cities of 10 million or more inhabitants. Most of the urban growth actually will happen at a lower scale of the city size distribution, and in particularly in very small and medium-sized cities. These small to medium-sized cities, where we even do not have a number estimate yet, we only have aggregated population estimations of people who live in these small and medium-sized cities. So these are cities, let's say, below 100,000 inhabitants or perhaps going up to 1 million inhabitants. These will be the main locus of urban growth, and at the same time, they also provide the biggest challenge. Because in these small cities, institutional capacities are extremely weak. We have no data, and we have no financial resources to address many, many pressing challenges. So this is one of the challenges, I think, also for the scientific communities, to come up with new tools that help to bridge this kind of gap. that we have the numbers and we have the policy attention and the scientists focusing on the mega cities like London, but nobody looks at the small cities. And we need really to think about how to find institutional configurations and techniques, combination of remote sensing with some kind of private sector data or whatever, to try to provide policy-relevant information also for decisions at this scale of a city of 100,000 inhabitants, somewhere in Africa or somewhere in Asia, where currently nobody looks at this kind of development trends. We also observe, obviously, a great heterogeneity in energy trends and in developments across different cities, and we are rediscovering a kind of frequent feature of systems, namely that systems portray path-dependent behavior. Where you are today depends on where you have started and on the development path which you have followed. You have here the historical trajectory of London, the city in which we are in here. So you see a clear kind of decoupling of economic from energy growth. So this is per capita energy use versus per capita income. We see a positive correlation until a certain point. This is basically the beginning of the 1970s, and then a complete decoupling. We have increasing wealth, but we have no corresponding increase in resource mobilization in terms of energy use. This is very different in rapidly growing countries in Asia, like shown here in the example of China with Beijing and Shanghai, again, two relatively well-studied cities, so where we have historical data. And another Chinese city, which is Hong Kong, I mean, a hybrid, formerly British, now Chinese city. But it also shows you the kind of large dispersion and the different diverse experiences which we observe at the urban scale. Now, of course, we have observed path-dependent behavior also at the national scale, so cities are, from that perspective, not very, very different. But the reasons and the explanatory factors of this path-dependent behavior at the urban scale remain further analytical and theoretical explanation. For the time being, we observe, but we cannot explain. At the national scale, we are a little bit better in theories and models that can explain this kind of path-dependent behavior. Let me move to the second cluster of main conclusions. This has to do with the energy and carbon footprints of urban areas. So there are some interesting findings there, but there are also some important caveats in this kind of domain, namely with respect to urban energy and CO2 accounting. Very important and interesting finding from our analysis is that we have what we have called in our assessment report an inverse sustainability gradient between the cities of the OECD countries and the developing country cities. So this shows you a sample from a database which we have built for our chapter. The data are posted online, so if you're interested to analyze them. So we have here a sample of 132 cities in Annex 1 countries, so these are the industrialized countries. And we show you here the cumulative population versus per capita final energy use. Now, clearly, you have a big dispersion, okay, from large to low. But the color code is the actually interesting piece of information here. Each time the color is blue, the per capita energy use of that city is significantly below the national average. Each time the color code is red, the per capita energy use of that city is significantly above the national averages. Okay? So when you look simply at this sample of OECD countries, you see that the dominant graphical impression is blue, meaning that many, many cities, most of the cities, actually have lower energy footprints compared to the national averages, which means cities are good for the environment. They're good because of specific effects which relate obviously to economic structure, which relate to density, which relate to the availability of public transportation modes, influencing transportation energy demand, etc., influence the energy demand in a positive direction, namely being lower than the national average. We can compare now this OECD experience with the same picture for our sample of cities in developing countries. So here, the sample size is smaller, only 68 cities, but obviously we have much larger populations, so the sample covers approximately 300 million people. And you see that the dominant color here is red. It means that cities in developing countries have generally over-proportionally larger per capita energy use compared to their national averages. Which means, again, we can explain it. There's some statistical analysis in the chapter, which you're welcome to read. Basically, the conclusion is that in the developing countries, the income effect, so the urban-rural income gradient in developing countries is particularly pronounced, and that is the main driver of the much higher per capita energy use in urban settings compared to rural ones. But this inverse, so in the OECD countries lower and in developing countries higher, I think is a very distinctive feature of urban systems, which we were not aware in that clarity prior to this assessment. So I'll leave it here for you to consider its implications further, which means we need to understand the full spectrum of urban energy demand in much more detail. We need to understand the income effects, the effects of density, the effects in policy leverages of urban infrastructures, etc. However, there is an important caveat, and this important caveat is shown in the next slide. Up to now, we have used a very simple system boundary to delineate an urban energy system, which is the direct final energy use. But of course, we can use also another system boundary, and that system boundary is not only interested in direct energy, but is also interested in embodied energy, gray energy, as this is called sometimes, because urban systems are inherently open. So they import energy, but sometimes in direct form, but many times they import energy already in embodied form, in goods and services, which these cities consume, importing from other areas, other cities, or rural hinterlands, and which basically means when you look at the embodied energy flow and you don't account it in an urban context, you have a risk of basically outsourcing a large part of the energy or greenhouse gas emission footprint. So these are a couple of estimates for some cities in Asia, and you see in these big megacities how important the embodied energy component is. In the case of Tokyo, more than 3/4 of the energy use of Tokyo is in fact in form of embodied energy, and we need to consider this embodied energy in addition to the direct energy flows which can be measured in a city. Now the problem of embodied energy is of course that this measurement is even more intricate than already the difficult measurement of energy flows. Recall, we have no statistics, so we need to provide some kind of constrained optimization models to produce these estimations. But for embodied energy, it's even more complicated because we have even less statistics. The statistics have enormous error margins. International trade data, for instance, are notoriously unreliable. There's a single data set which exists. It's the GTAP database. There's a kind of global general equilibrium model database set in which, for instance, when you look at the detailed trade flow analysis and data in that database, you find error margins up to a factor of 10. So we have a big challenge ahead of us in arriving at comprehensive accounts of urban energy and carbon footprints. Again, an important conclusion that this is something which will remain on the scientific agenda for many, many years to come, and there is no definitive conclusion in terms that this system boundary is preferable over another system boundary. We need multi-layer system boundaries in order to understand urban systems. And this is, of course, both a challenge for our models, this is a challenge for our science, and this is, above all, a very big challenge for our data, and we need to confront this. Let me move on to the next block of principal conclusions. Obviously, this is not a major conclusion. Most of you will be familiar with that, perhaps not in its extreme formulation. Cities have specific sustainability challenges and opportunities. And one of the most important implications of the specificity of cities is that their high density enables new options for demand and resource management, but also imposes new constraints. High density imposes severe new constraints on energy systems, namely, in an Arnaud-esque kind of summary, high density means zero impact systems, not low impact systems. Because even low impact system, clean natural gas, catalytic converter cars, if at appropriate high densities, which we observe in big cities, overwhelms the dissipative capacity of the local environment and therefore poses significant environmental burdens. A second observation, and this observation was not very popular amongst some of our green colleagues, is that the other side of the high density question of urban areas is that the potential contribution of locally harvested renewables is minimal. According to our assessment, perhaps 1% of the energy demand of urban areas can be satisfied by renewables produced in that urban areas, which means the idea of larger system boundaries, of interconnected system, but also the need for benchmarking and monitoring and quality assurance of the environmental and social conditions under which the imported renewable energy flows arrive at a city need much further scrutiny and analysis. I give you two illustrations here. This is a three-dimensional map of air pollution exposure. So this is a very simple concept which we have borrowed from our nuclear friends. So this is air pollution times people exposed to that level of air pollution. And you see the enormous spikes in the large agglomerations as a twin result of high ambient concentrations of traditional air pollutants, sulfur dioxide, particulates, you name it, and also of high population density. This is clearly one of the most significant threats for human health. And as subsequent analysis in other chapters of the global energy assessment has shown, it is the area of the most significant and most substantial co-benefits of climate mitigation. The nexus between climate mitigation, reduction of traditional air pollutants, and quantified and quantifiable impacts on human health is the major story to sell climate change mitigation to developing countries. It's a human health impact story. It is not a 2-degree warming limit story or avoiding climate damage is very far out in the future. It is a story that through climate mitigation you can have near-term real benefits on human health. And chapter 17 in the global energy assessment, together with the health chapter number 4, has produced some quantitative estimates on this kind of health benefits of climate mitigation. And I think this is something new, which we knew in principle, but in this kind of quantification, quantified framework, is a new finding also from this assessment. Here I show you some of the stuff I do together with colleagues at YASA. We try to do spatial explicit models. This is one of the attempts of downscaling energy use at the European scale at the grid level. And what I show you here is a simple representation. I'm sorry the covers do not show so nicely on the slides than they do show on paper, but I think you get the basic gist. You have the population distribution. So the darker a grid cell, the darker is the population density, shown here. And then we have different color codes referring to the energy demand, which is expressed in watts per square meter. So this is the spatial energy demand. And then, of course, if you move to hotter colors, that means you have a higher energy demand. Now, all what I want to leave with you is to look at the blue areas here. Don't look at the white areas. The population density is so low there that it doesn't matter. Okay. The blue area here, this is where the energy demand is below 1 watts per square meter. And that's basically a ballpark where you can meet the energy demand locally by renewables. Whatever is not blue here, the energy demand is several-fold, sometimes 100 times larger than the maximum renewable resource potential at the local level. That means it can never be supplied by renewables. If you do the mathematics, 80% of the energy demand in Western Europe, and 2/3 of the energy demand in Eastern Europe is above this renewable threshold. So is above 1 watts per square meter. That means cannot be supplied by locally harvested renewables. So renewables need to be harvested somewhere else and then brought into the urban centers. So quite ironically, or perhaps not ironically, future renewable-dominated energy systems will look from an infrastructure perspective not too dissimilar from traditional centralized fossil energy systems. This is not what the people who push for renewable energies really want to hear, but in this assessment they hear it. And I think it's an important aspect which we need to consider when we plan for renewable resources. It's not only a question to plan for the resource, it's first of all a question to plan for the infrastructure. And the infrastructure challenge is not only because of intermittency, it is first of all because of the spatial energy supply density mismatch, which is the most pronounced for urban centers. Let me now also illustrate you one of the unique challenges and or opportunities which we have at an urban scale. The urban systems are very messy. They're very multifarious. A lot of things happen. But in the language of economics, this complexity can be reduced to decisive advantage. It's called economies of scope. Now, the energy engineer knows this by cogeneration, district heating systems, heat cascading system or similar. So these concepts are known to the engineer for many, many years. We don't need fancy terms from the economics on economies of scope. But they are an important illustration of the unique opportunities which an urban system provides in an energy context. Now, I cannot bring doves to Athens or the Catholic Church to Rome. So I'm not going to mention the enormous synergies which exist outside the energy systems proper. And David can give you a whole lecture on this. There are enormous potential synergies in co-optimizing energy systems with water systems, for instance. We all know the enormous benefits of co-optimized transportation systems, not of individual transport modes, but entire logistical chains or trip chains of entire systems. Because after all, every mobility is never assured by a single mode. You all ended up in this room by walking. So the end point is always soft mobility by walking. So this is also often forgotten. So we need always to think about different transportation modes, how they interact to deliver a final purpose, which means a source destination traffic of people or goods. And so therefore the systems perspective can be very fruitfully and very valuably be extended beyond the narrow energy realm. We can talk about systems of energy and water, systems of transportation systems, etc., and linking that at an urban scale. I show you here a flow diagram of my home city. It's the city of Vienna. I don't show it simply because, Vienna is, is my home city and I'm patriotic. Vienna is a socialist city, okay? It's one of the last remaining socialist cities, so if you're ever there on 1st of May, go out there, you will have 100,000 people on the 1st of May march organized by the Socialist Party. You cannot see that in any communistic country except North Korea anymore, but you can see it in Vienna. One of the energy legacies of the socialistic city government, which actually produces an extremely functional social infrastructure and also technological infrastructure, is, for instance, that Vienna has an extremely large and ambitious cogeneration scheme and district heating grids, which are now extended also to district cooling grids. And we can show the efficiency implications of this grid. Cogeneration in the city of Vienna reduces the energy demand by approximately 15%. So it's quite significant. At the same time, we have here flows which are relatively detailed, which lend themselves to the classical thermodynamic engineering analysis of exergy analysis. And so here are a couple of numbers, of illustrated numbers. So here you have the city of Vienna. Now, when you look at Vienna in terms of first law efficiency, the energy system of the city of Vienna, because of high cogeneration, has an efficiency, first law efficiency of 50%. That looks fantastic. Nothing to do anymore for the engineer. When you look at it in terms of second law analysis, you see that the actual efficiency of the system is only 17%. So vast room for improvement in efficiency. When you compare other cities, London is here, Geneva, Malmö, obviously the numbers vary a little bit because the details of the analysis and the data are, of course, a little bit different, and there is no unified methodology yet established. But we all are in the same ballpark of 10 to 20%, which means we can improve the efficiency from a thermodynamic perspective of energy use in an urban context between a factor of 5 to 10. That urban, again, is better than rural, I show you here with a comparison of an exergy analysis of a traditional Mexican village, which has an exergy efficiency of less than 6%. So at least a factor of 2 lower than that of a modern industrial city. So again, unique opportunities at the urban scale. However, there's again, like always, a downside. To harness these efficiency potentials, we need much more system integration. And that's, of course, not an easy thing to do. Let me move to the last conclusions. We have vast improvements, but most require management of urban form and systemic change. So we do not need dedicated energy policies, we need integrated policies at an urban scale. But at the same time, we face what we call a governance paradox. The largest potential is from systemic change and from integration of land use with transportation and energy and water policies, but that's also the most difficult to do because our decision-making landscape is very, very fragmented, and many cities don't even have any leverage over many of the infrastructures because they are in the private sector. So it's an incredible coordination task which remains. This did not make it into the report. This is my own summary. It's a stylized summary, but for the sake of an argument, please live with this stylized summary because there are, of course, always some exceptions to the stylization of hierarchies. But the basic message, I think, should become clear. When we rank different options to make cities more sustainable in the energy space, we have here a hierarchy of what matters in terms of energy flows. How can we influence energy flows? And we have an inverse hierarchy of what we can influence by urban scale decision-making process. So what we can influence the most, it is actually what matters the least in energy terms. And what matters the most in energy terms, which we can actually influence the least by decision-making at the urban scale. A city like London is not member of the WTO negotiations on international trade, and so therefore, but international trade, division of labor, is, as it turns out, one very, very important determinant of explaining differences in energy use, simply because of differences in economic structure. But this kind of mismatch or governance paradox is one of the interesting aspects of urban systems, which make them very, very complicated, but also interesting to analyze. And obviously, there's always middle ground, where you can have also a relatively great impact on urban energy, like here on urban form, and you also have a not unsubstantial public policy or urban policy leverage, like, for instance, on public transportation schemes. In order to illustrate this, we have drawn on a model developed here at Imperial College, okay, the Sin City model. And this model is ingenious, okay? I'm not involved in the modeling, so I can praise the model. It's ingenious for two reasons. First is the name. It invites confusion. I misspelled it in the report consistently between Sin City and Sim City and so on. So it is a name which the sociologists or the social scientists and you will recognize as interpretive flexibility. So quite ingenious from that aspect. Okay. The second ingenious aspect is that it is, I think, a prototype of a new generation of models. A new generation of models that breaks traditional disciplinary boundaries in operations research, because it combines traditional optimization techniques with spatially explicit models as well as agent-based modeling approaches. It's definitely not the last model to be developed in that area, and I'm sure it has enormous room for further developments and improvements, but I wanted to highlight it, especially to the younger colleagues, because this is something which I think is really the forefront of research. It's this kind of transdisciplinary combination of different approaches to try to understand and do justice to the messiness and complexity of urban systems. Now, in this model, and that's why we use models, it's not that the model hopes to be able to replicate the complexity of an urban system, but a model allows us to do controlled experiments, which we cannot do in reality. Nobody, well, you know, we have done some experiments. You know, the congestion tax in London was one of the experiments, but it's not a very massive experiment in energy systems. But models we can subject to very extreme experiments. And this is exactly what we have done in these model simulations. So this is all a synthetic city. And then you simulate extreme policy measures. So in one case, sorry for that, okay? In one case, you focus only on improving the efficiency of the building design, the thermal integrity of the building. In another one, you only focus in optimizing energy-wise the density and the layout of the city. So you focus only on urban form, okay? And obviously, you also have an optimized solution. So basically, it allows you to rank different measures in a very controlled experiment way. And as it turns out, this kind of hierarchy of policy leverages and impacts, which I have mentioned earlier, were also confirmed in the model simulations. The biggest impacts are from efficiency of energy and from urban form, and conversely, the energy sector optimization, for instance, through complete decentralization and cogeneration systems, are significant, but are not as important. So it's not 50% as in the other cases. It's more in the tune of 15%. That's why we do the models. We want to find out what matters more than what matters less, and then obviously also find out a little bit about the complexity of make system change happen. It's much easier to make this happen in a model than in the actual reality. So with this, I recap the main conclusions and want to thank also all of the authors of this voluminous report on urban energy systems and look forward to our ensuing discussion. Thank you very much.